May 12, 1941, 7:15 p.m. American mathematics professor Howard Aiken stared in utter disbelief at the classified intelligence reports from Berlin. In an unassuming living room in Berlin, a German civil engineer named Konrad Zuse had created something that would shake the scientific world to its core: the Z3, the world's first fully automatic, program-controlled computer. Aiken's hands trembled as he read the technical specifications: 2,000 electromechanical relays, 22-bit floating-point arithmetic, fully binary logic. America was 20 years behind. What Aiken didn't realize in that moment was that Zuse had not only built the world's first computer, but had also simultaneously invented the programming language of the future, perfected the binary system, and foreseen the entire architecture of modern computers. While Americans were still fumbling with mechanical calculators, and the British were developing their first primitive vacuum tube computers, the Z3 was already crunching complex engineering tables in seconds. The story begins in 1935, when Konrad Zuse, a 25-year-old civil engineer in Berlin, was frustrated by the endless mathematical calculations required by his work. Static calculations for bridges and buildings meant hours of manual labor with mechanical calculating machines. Zuse dreamed of a machine that could take over this monotonous work. What he didn't know was that he was about to ignite the digital revolution. In his parents' apartment in Berlin-Kreuzberg, Zuse began building his first mechanical calculating machine, the Z1. Even here, his brilliance was evident. While all other engineers were working with the decimal system, Zuse intuitively recognized the superiority of the binary system: 0 or 1, electricity or no electricity, magnetized or not magnetized. This simple logic would become the foundation of all future computers. The Z1 was a mechanical marvel made of 30,000 individual parts, completely cut from thin sheets of metal and assembled by hand. Zuse developed a mechanical memory that could store 64 22-bit numbers, a concept that would only become known as RAM memory decades later. Input was via a keyboard, output via panels of lights, a user interface that was light years ahead of its time. But the mechanical Z1 was too prone to failures. Zuse's genius was revealed in his next step, the transition to electromechanical technology. While American engineers would still need years to understand the reliability of electrical circuits, Zuse began building the Z2 in 1938, which already used telephone relays as switching elements. The Z2 was a hybrid model: mechanical arithmetic unit, electromechanical control unit. Here, Zuse developed the world's first program-controlled architecture. Programs were punched onto perforated film strips, an idea inspired by jacquard looms, but revolutionary for computers. Zuse realized that the same computer could solve different tasks depending on which program it loaded. In 1939, as Europe plunged into war, Zuse completed his Z2. The machine could already execute simple programs and perform mathematical operations. But Zuse knew this was only the beginning. He dreamed of a fully electromechanical machine that could solve all the calculation problems of his time. The war brought unexpected opportunities. The German aviation industry urgently needed solutions for complex aerodynamic calculations: aircraft wings, fuselage shapes, drag calculations, all tasks that occupied hundreds of engineers for weeks. Zuse received financial support from the Henschel Aircraft Works and the German Aviation Research Institute. With this money, Zuse built his masterpiece in 1941, the Z3. 2,000 telephone relays, each one soldered by hand, formed the heart of the machine. The arithmetic unit worked with 22-bit floating-point arithmetic, a precision that was unimaginable at the time. The control unit could read programs from film strips and execute complex command sequences. The memory held 64 words of 22 bits each, tiny by today's standards, but revolutionary for 1941. The technical data of the Z3 reads today like the birth certificate of the digital world. Clock frequency 5 to 10 Hz. Addition time 0.8 seconds. Multiplication time 3 seconds. Laughably slow by today's standards. But in 1941 it meant this. What an engineer calculated in 8 hours, the Z3 accomplished in a few minutes. The first test of the Z3 on May 12, 1941, became a historic moment. Zuse entered a complex matrix calculation that would normally have occupied a mathematician for several days. The relays clattered, the lamps flickered, and after a few minutes, the machine spat out the correct result. Konrad Zuse had just ushered in the age of computers. What the Allied intelligence services didn't know, Zuse was developing the world's first higher-level programming language in parallel with the hardware, the plan calculus. This language already contained all the concepts of modern programming: subroutines, conditional branches, loops, even recursive calls. Concepts that IBM and others would only develop in the 1950s. The American computer scientist John von Neumann later described the von Neumann architecture as the basis of all computers. In fact, Zuse had already described this architecture in his first designs in 1936, a computer with shared memory for programs and data, an arithmetic unit, a control unit, and input-output devices. Von Neumann merely discovered what Zuse had already invented a decade earlier. The tragedy of the Z3 began in 1944. Allied bombing raids destroyed the Berlin laboratory where the Z3 stood. With it vanished the only working copy of the world's first computer. Zuse rescued only the construction plans and his programming language, plan calculus. The original was lost, but the ideas would survive. 1945, the war ended. And with it began the greatest technology plunder in history, Operation Paperclip. American and Soviet commandos scoured Germany in search of scientists, engineers, and their inventions. Zuse narrowly escaped capture and hid his documents in a small Bavarian village. The irony of history. While the Allies were desperately searching for German rocket technicians and nuclear physicists, they completely overlooked the inventor of computer technology. Zuse remained undisturbed in his hiding place, dreaming of new machines. Meanwhile, the Americans were feverishly developing their own computers, unaware that a German had already invented everything. In 1946, the University of Pennsylvania proudly announced the completion of ENIAC, supposedly the world's first electronic computer, weighing in at 30 tons, using 18,000 vacuum tubes, and occupying 1,500 square feet. It was a monument to American engineering. The press hailed ENIAC as an electronic brain, destined to revolutionize the future, but there was something the American engineers weren't saying. ENIAC could calculate, but it couldn't store programs. For every new task, technicians had to spend days rewiring cables and flipping switches. The German Z3, 5 years earlier, could already do everything ENIAC couldn't: load programs, store them, and execute them automatically. By 1947, American engineers were working feverishly on EDVAC, the first stored program computer. They touted the revolutionary concept of storing both programs and data in the same memory. John von Neumann was celebrated as a genius, but no one mentioned that Konrad Zuse had already described this concept in 1936 and built it by 1941. The truth only came to light in 1967 when historians studied Konrad Zuse's notebooks. His designs from 1936 clearly showed the complete computer architecture. the architecture that von Neumann presented as a revolutionary invention a decade later. Zuse's plan calculus contained programming concepts that Fortran and COBOL wouldn't implement for years. In 1969, this revelation led to one of the most spectacular patent disputes in the history of technology. The question, who really invented the computer? After years of investigation, an American court ruled that John Atanasoff and not the ENIAC developers had built the first electronic computer. Konrad Zuse wasn't even mentioned. It was too embarrassing for the Americans to admit that a German was decades ahead. Today, every computer in the world operates on Zuse's principles: binary logic, program storage, floating point arithmetic, the separation of arithmetic and control units, all concepts from the Z3 in 1941, Apple, Intel, Microsoft, Google. They all build on the foundation laid by a German civil engineer in a Berlin living room. Modern computer science is full of terms that describe Zuse's ideas, but under different names. The Harvard architecture distinguishes between program and data storage. Zuse had already built it that way in 1938. The Princeton architecture uses shared memory. Zuse's Z3 already worked that way. Object-oriented programming, structured programming, compiler technology, all described in Zuse's plan calculus from 1945, particularly bitter. The programming language ALGOL, celebrated as a revolutionary breakthrough in 1958, was practically a poor copy of Zuse's plan calculus. Concepts like data types, block structure, recursive procedures. Zuse had already defined all of that mathematically and precisely in 1945. The ALGOL developers knew Zuse's work, but they never mentioned it. Modern supercomputers use floating point arithmetic according to the IEEE 754 standard. This standard is based on concepts that Zuse had already developed in 1938. His 22-bit representation with sign mantissa and exponent was the direct precursor to all modern floating point systems. The Silicon Valley legend of garage inventors who revolutionized computers hides an embarrassing truth. The fundamental computer concepts weren't invented in California, but in a Berlin living room. Steve Jobs and Bill Gates built on foundations laid by a German engineer 40 years earlier. It wasn't until 1998 that the German Museum of Technology reconstructed the Z3 using the original documents. The rebuilt computer worked perfectly, proving that Zuse really did build the world's first functional computer in 1941. Computer science students from all over the world now make a pilgrimage to Berlin to see the machine that started it all. These stories aren't just dusty archives or forgotten patents, they're the foundations of our digital world. Every smartphone, every laptop, every supercomputer works on principles that a German engineer invented over 80 years ago. Real innovation, real genius, real consequences for billions of people. This story of German engineering must never be forgotten. If these technical truths are important to you, then support me with YouTube's super thanks. The golden heart below. Every super thanks allows me to dig deeper into archives, to digitize rare blueprints, to interview the last surviving engineer witnesses. Help me preserve this technical history for future generations. But the story of the Z3 reveals an even deeper truth about German engineering. Konrad Zuse didn't work in a vacuum. He stood on the shoulders of a centuries-old tradition of German precision and innovation. From Gottfried Wilhelm Leibniz, who invented the binary system in the 17th century, to Carl Friedrich Gauss, who laid the mathematical foundations of information theory, to Hermann Hollerith, who developed punch card technology. German thinkers prepared the ground for Zuse's triumph. The Z3 story also shows the typically German approach to technical problems. Zuse systematically analyzed the weaknesses of mechanical calculators, developed theoretical solutions, and then implemented them with Prussian thoroughness. No quick workarounds, no superficial improvements, but a complete reinvention of calculation from the ground up. American computer development was often project-driven and militarily funded. ENIAC was created for artillery calculations, EDVAC for the Atomic Energy Commission. German innovation, on the other hand, sprang from individual curiosity and the desire for elegant solutions. Zuse simply didn't want to calculate by hand anymore, and in doing so, he revolutionized the world. These different approaches are still reflected today. German software is known for reliability and thoroughness. American software for marketing and quick market launch. SAP, Siemens, Bosch. German technology companies focus on long-term quality, not on quick profit. Zuse's influence extends far beyond computers. His systematic approach to complex problems, his ability to translate abstract mathematical concepts into practical machines, his understanding of the elegance of simple solutions. These are principles that shape all of modern technology. Modern artificial intelligence is based on neural networks, which ultimately only perform very complex binary calculations. Every deep learning algorithm, every AI application, every machine learning system works on computers that operate according to Zuse's principles. Without the Z3 of 1941, we wouldn't have ChatGPT, autonomous cars, or speech recognition today. Blockchain technology, which underpins Bitcoin and other cryptocurrencies, is essentially a network of computers performing complex cryptographic calculations. These calculations run on processors that are direct descendants of Zuse's Z3. Modern quantum computers may use different physical principles, but their programming and control rely on classic computers. Zuse's legacy lives on. The internet revolution of the 1990s would have been impossible without powerful computers. Routers, servers, personal computers, all are based on the von Neumann architecture, which is really the Zuse architecture. The World Wide Web exists only because a German civil engineer laid the foundation in 1941. Modern smartphones are computers that are millions of times more powerful than Zuse's Z3, but operate according to the same fundamental principles: binary logic, stored programs, floating point arithmetic. The iPhone in your pocket is a direct descendant of the machine that ushered in the computer age in a Berlin living room. The technical details of the Z3 were so far ahead of their time that even today's computer science students are astonished. The floating point format, with 1 bit for the sign, 7 bits for the exponent, and 14 bits for the mantissa, was mathematically elegant and practically efficient. Modern floating point standards like IEEE 754 use the same basic principles, just with more bits for higher precision. Zuse's relay technology was a masterpiece of electromechanics. Each of the 2,000 telephone relays switched in about 10 milliseconds and had a lifespan of several million switching cycles. This reliability was crucial. A single defective relay would have paralyzed the entire computer. Zuse's systematic approach to fault tolerance and maintainability set standards that are still relevant today. The architecture of the Z3 was revolutionary in its simplicity. The arithmetic unit for arithmetic operations, the control unit for program execution, the memory for data and programs, and the input to output devices. These 4 basic components still define every computer today. From supercomputers to microcontrollers, they all follow this schema. Particularly noteworthy was Zuse's understanding of programming languages. His plan calculus contained concepts that only found their way into other languages decades later. structured programming with if-then-else constructs, while loops, procedures with parameters, even primitive object-oriented programming. All of this was mathematically defined as early as 1945. The timing characteristics of the Z3 showcase German engineering at its finest. Addition and subtraction took 0.8 seconds, multiplication took 3 seconds, division took 4.5 seconds. These times were hard-coded and absolutely predictable, a concept known today as real-time computing, which is essential in critical systems. Zuse's memory concept was groundbreaking. The mechanical memory of the Z1 with its rotating metal sheets was too unreliable. So he developed an electromechanical memory with relays for the Z3. Each bit was represented by the state of a relay, the direct precursor to modern flip-flop circuits in digital memories. The input-output systems of the Z3 set standards for human-machine interaction, the decimal keyboard for number input, the lamp fields for result display, the film strip reader for programs. These components established the concept of different I/O channels, which live on today in USB, HDMI, Ethernet, and wireless protocols. Zuse's mathematical brilliance is evident in his handling of special cases, division by zero, overflow conditions, undefined operations. The Z3 had elegant solutions for all of these problems. Modern exception handling and error recovery are based on concepts that Zuse had already implemented. The manufacturing quality of the Z3 was typically German. Every relay was individually tested, every solder joint checked, every mechanical component measured for tolerances. This quality assurance was essential for functionality and established standards that continue to distinguish German engineering products today. Operation Paperclip missed Zuse, but found his competitors. Dr. Helmut Hölzer, who was responsible for the V2 guidance computers, was brought to America and developed analog computers for NASA there. His expertise flowed directly into the Apollo program. The irony: German computer technology took America to the moon. The Soviets were more systematic. They kidnapped entire research teams and forced them to work in Soviet labs. German computer engineers developed the first Soviet mainframe computers, which were presented as completely Soviet inventions. The BESM-1 of 1953 was directly based on German designs. IBM benefited indirectly from German innovations. Many of the engineers who worked on IBM's first computers had studied German technical literature, or were Germans recruited through Operation Paperclip. Concepts like stored program architecture and binary arithmetic found their way into American designs. The transistor revolution of the 1950s built on Zuse's foundation. Transistors replaced relays. Integrated circuits replaced discrete components. But the logical structure remained the same. Modern processors with billions of transistors still perform the same binary operations that Zuse realized with relays in 1941. Zuse's influence on modern programming languages is often overlooked, but fundamental. Fortran, from 1957, adopted Zuse's concept of mathematical expressions in program code. Algol 60 copied Zuse's block structure and scope rules. Pascal, C, and their successors are all intellectual descendants of the plan calculus. The development of operating systems followed Zuse's architecture. The separation between system and application programs, the management of memory and peripherals, the scheduling of processes, all these concepts were already present in Zuse's work, even if he didn't fully implement them. Modern compiler technology is based on Zuse's ideas for the automatic translation of higher programming languages into machine code. His mathematical notation in the plan calculus was so precise that it could be translated directly into executable code. the basic principle of all compilers. The Internet protocols, TCP/IP, use binary encoding for all data. Every bit that flows through the Internet is processed according to the same binary principles that Zuse developed. Without Zuse's binary logic, there would be no modern Internet. Cloud computing is essentially the distribution of Zuse's computer concept over networks. Amazon Web Services, Google Cloud, Microsoft Azure. They all offer computing power, storage, and programs as a service, exactly as Zuse envisioned for the future. Artificial intelligence systems like GPT, BERT, or modern neural networks run on GPU clusters consisting of millions of processor cores. Each individual core is, in principle, a highly optimized descendant of Zuse's Z3, performing binary operations with unimaginable speed. Quantum computers represent the next revolution, but even they require classical computers for control and programming. The quantum software is developed on computers, operating according to Zuse's principles. Even the quantum mechanical superposition uses binary states as its foundation. The technical specifications of the Z3 in detail reveal the full extent of Zuse's genius. The word length of 22 bits was optimally chosen, sufficient for engineering mathematical precision, but not so long that the relay hardware became overly complicated. The floating point format allowed numbers from approximately 10 to the power of 38 to 10 to the power of plus 138, a range that was sufficient for most technical calculations. The instruction set of the Z3 was minimal but complete: addition, subtraction, multiplication, division, square root, conditional jumps, and memory operations. These 8 basic commands were sufficient to implement any conceivable algorithm, a testament to Zuse's mathematical penetration of the problem. The memory system was hierarchically structured. Decades before this term was coined, 64 words of RAM for current calculations, unlimited program storage on film strips, and an accumulator for intermediate results. This architecture is found today in every processor, registers, cache, main memory, permanent storage. Zuse's mechanical precision was legendary. The Z1 consisted of over 20,000 hand-cut sheet metal parts, each with tolerances of less than 0.1 millimeters. Without modern manufacturing machines, only with a fret saw and file, he created mechanical computers of incredible precision. This craftsmanship established German standards for precision mechanics. The programming of the Z3 was done in a notation that anticipated modern assembly languages. Each command was punched as a whole combination on 35mm film material. This physical encoding was robust and durable. Many original Zuse programs are still readable today, while modern data carriers have become unusable after decades. Zuse's documentation was exemplarily thorough. His notebooks contain not only the final designs, but also all considerations, alternatives, and discarded approaches. This systematic approach enabled later engineers to understand his thought processes and build on his ideas. The maintenance of the Z3 was carried out according to German industrial standards. Every morning, each relay was tested individually. Defective components were replaced immediately. All mechanical parts were oiled and adjusted. This preventive maintenance was essential for reliable operation and established principles that are applied today in data centers worldwide. Zuse's cost efficiency was remarkable. The entire Z3 cost about 25,000 Reichsmarks, roughly the price of a mid-range car. In comparison, the American ENIAC cost $500,000. Inflation adjusted, over $10 million today. German engineering was not only technically superior, but also economically more efficient. The energy efficiency of the Z3 was far ahead of its time, 4,000 watts of total consumption. For the complete computer, less than a modern hairdryer, the ENIAC required 150,000 watts and consumed as much power as a small town. Zuse's relay technology was not only more reliable, but also environmentally friendlier. The user-friendliness of the Z3 set standards for human-machine interaction. The keyboard used the familiar decimal system for input. Even if calculations were done internally in binary, the output was via lamp fields. In readable decimal numbers, this abstraction between user interface and internal processing is a universal standard today. Zuse's error handling was revolutionary. Division by zero did not lead to a system crash, but to a defined error message. Overflows were detected and signaled. This robust error handling was essential for practical applications, and decades ahead of American systems that simply froze on errors. The modularity of the Z3 design allowed for easy repairs and upgrades. Defective relay groups could be exchanged as a unit without disassembling the entire computer. This modular architecture is standard today in all electronic systems, from smartphones to supercomputers. Zuse's testing methods were systematic and thorough. Each component was tested individually, then in subsystems, finally in the complete system. Test programs checked all mathematical functions and boundary cases. This structured quality assurance established methods that are essential today in software development. The scalability of Zuse's design was remarkable. His Z4, built in 1945, already had 1,024 words of memory and expanded commands. This ability for systematic improvement showed that his architecture was fundamentally sound, not just a clever trick, but a solid basis for further developments. Zuse's documentation of his algorithms was mathematically precise and practically implementable. His description of the floating point arithmetic was so exact that modern computer engineers could directly implement hardware from it. This clarity and precision in technical documentation became the German standard. International recognition came late, but definitively in 1998, the IEEE Computer Society named the Z3 a milestone of computer history. The Computer Museum in Boston exhibits Zuse's work on an equal footing with ENIAC and EDVAC. Stanford University teaches Zuse's contributions in computer science foundation courses. The truth prevails, even if it takes decades. Modern blockchain technology is based on the same binary hash functions that Zuse used for memory addressing. Cryptographic algorithms use the Boolean logic that he had perfected. Without Zuse's fundamentals, there would be neither Bitcoin, nor modern encryption, nor secure online communication. Virtual reality and augmented reality systems process in real time millions of floating point calculations per second. Each single one of these calculations follows the mathematical rules that Zuse developed for his Z3. The immersive worlds of today stand on the foundation of a Berlin living room from 1941. Autonomous vehicles. They contain dozens of specialized computers for sensor processing, navigation, and vehicle control. These embedded systems, they use the same architectural separation between processing, memory, input, output, and control that Konrad Zuse first implemented. Self-driving cars. They're essentially rolling descendants of the Z3. The story of the Z3, it shows that true innovation often arises from simple needs. Zuse simply didn't want to calculate by hand anymore, and in doing so, he invented the foundation of our digital civilization. Today, we live in a world that would be unthinkable without his invention. And most people, they don't even know his name. This technological revolution, it was made in Germany, born from German thoroughness, German precision, German engineering spirit. From a living room in Berlin to global digitalization, a story that shows how a single, ingenious idea can change all of humanity. What German technology has surprised you the most? Many engineers in the comments, they've pointed out incredible connections. Grandfathers who worked at Zuse, blueprints in company archives, modern patents with German roots. Share your technical discoveries. Every comment, it's a piece of the puzzle of technological history.